Setting up recording. Yeah, welcome everyone. Today we are on week 14 of the Qubit by Qubit Intro to Quantum Computing course. I'm gonna be, one second, I need to get everything set up for the recording. But yeah, today we're going to be going through the block sphere, which I know I've mentioned many times throughout both this semester and last semester because I couldn't help myself, and it is just a really useful visualization for our qubit states. We're going to be going into more explicit math behind it rather than the kind of like high level, here's a picture, here's where our state is going that we've done previously. So as usual, we have the attendance quiz passcode in the bottom right-hand corner of every slide. And I'm going to go through logistics this week just as a reminder, and then do the same like attendance quiz, feedback, etc. as usual. So I just want to remind everyone that there are student assistant office hours from 8 a.m. to 2 p.m. Eastern Standard Time every Friday, and then also 10 a.m. to 12 p.m. Eastern Standard Time on every Sunday, and that's same as UTC -5 if you don't know US time zones. I think everyone in this section is US based, but I'm not 100%. I was told that at one point, and then I was told that wasn't true because people got moved around, so I don't know what's the case, but I try to keep things general just in case. Yeah, this is just a great resource to learn from other students. It's a good opportunity for people. Like also, if I think there was like a call put out at some point, like if you were interested in being one of these student assistants, if you had more background in the area. But it is like a great resource to just like talk to other students and have kind of a lower key opportunity to ask questions. Similarly, there are homework review sessions every Friday from 4 to 5 p.m. EST. And this is with one of the instructors. And the most important thing on this slide, like which is I guess resource related for like, or I guess it is kind of a resource. It's something you need to do is to create your IBM Quantum Experience accounts. The instructions are on Canvas, so check there. We will be using IBM Quantum Experience starting next week to actually program IBM's quantum computers. So if you don't want to miss out on programming IBM's quantum computers next week, make sure to set up your account now. There are some logistical issues with it, like you have to be over like a certain age or whatever to just like sign up. So you're supposed to have like your parent approve that you're doing it and all these things. So definitely try to get that squared away within the next week before we're actually trying to do it in real time. Okay, so I have the Canvas attendance quiz again in the bottom right-hand corner of every slide. And this week, I guess we have the same quiz as last week, or I think. Like if you're glad we took the time to learn the math concepts inherent to quantum computing, I think this is the same quiz as last week, but I'm not. I might be crazy because I was told we have a weekly TA meeting where we go through everything. So maybe I'm wrong, but I feel like it's the same. But yeah, so that is our quiz for the week. And we also have our pre-lab Zoom feedback. Let me start that. So this is the usual scale from 1 to 5, how well you understood the lecture material, which was on the block sphere. I know it was a little bit more math heavy than usual. And I was told that it was maybe a bit quick. So, oh, the attendance quiz that is actually on Canvas, it seems like I'm hearing in the chat, is different than what is on our slide. I guess our lead TA may have just forgotten to update it on the slide. But yeah, whatever is there is what's actually there. I'd never used IBM's quantum experience substantially until I started working with Qubit by Qubit, because I don't do like theory work, or I guess like theory work that like runs on like other people's hardware. Like I make my own hardware. So yeah, it's a fun resource though. So I'm getting I'm getting a lot more 4s than usual for this week's material. So I'll try to like take that into account and definitely ask questions, especially if like you just don't understand like one step in the math. Like sometimes it's very simple where it's a factor of 2, and if you don't notice it, you'll get very confused. So even if it's like a trivial question, like with a trivial question, there's a trivial answer, and so it won't take very much time. And if it's a non-trivial question, then we can go into depth, and it will like either way, like it's a good thing to go through. So generally, like it does seem like maybe you guys are overall a little less comfortable with material from this lecture. So hopefully we can try to make that better with this lab. Yeah, okay. So last week we had a lot of questions about phase, and we're going to see this kind of in 3D on the block sphere. But for now, I want to go to 2D with something that you guys have definitely seen a lot with a clock. And I guess analog clocks are a little less common now than they used to be. But if you are trying to, you can put a number to the phase of every hand on this clock. So if you have to choose a reference. And so typically we choose our reference to be like at 12 o'clock. And so if you want to find the phase of our minute hand, that would be this angle between 12 and 2. Similarly, we could do this as second hand, which would be the angle between 12 and 5. We'll use a phi for that. And then we can also do the angle between 12 and 10 to the hour hand. So that'd be all the way around. This is like a really ugly circle. And I guess I don't know what to use for the third angle measure. I'm used to only having 2. What symbol do I want? I'm gonna do a chi. We're gonna do chi as the third one. These are all just Greek letters. They're nothing intimidating. That's one thing I do like to try to note, that all these are just symbols that we've chosen that are commonly used to represent angles. I mean, chi really isn't. I just needed a third one, but theta and phi, like this guy's theta, this guy's phi. Those are very commonly used to represent angles, and we just use them because we need some symbol that we can distinguish from other symbols. So if we're already using X, Y, and Z for our position, then we need something else for our angle. And maybe like we're using F and G and H for functions very commonly. So we've used up a lot of the typical like Latin letters, and so we've moved on to Greek. That's the only reason we're using these. There's no special meaning to that. So this is how we would calculate the angle or the phase of a time relative to our like global reference. That's, you always need to have some position to reference your angle to, similarly to how you need to have some position to reference, or some position to reference a position to. If we have a point in space, I'm going to put a number to it. Well, I could just say, oh, this point is 5. What is 5? Where is 5? Well, 5 becomes meaningful if we put some kind of axis, and we're like, this is actually 5 on the x-axis, and maybe it's also 5 on the y-axis. And we just chose to only use one number to describe it because we were trying to be efficient, but we really didn't explain anything. So the exact same way, we need to have some point of reference for our angle. And so what you may have heard in lecture this week is the concept of relative phase. So instead of referencing something to what we've chosen, like this point to be our global reference, we can instead have I guess you could call it like a local reference or like a relative reference. So if you're trying to calculate instead, I'm going to choose, I only have one more color. I'm going to use orange. if you want to find the relative phase between your minute hand and your second hand, you can do that with this, that would be this orange line. I've long since run out of symbols to use. I'm going to use like that one. It's a theta, maybe? It's some Greek letter. Or is it a Z? I don't remember. Well, it's that thing. And that's the relative phase between your minute hand and your second hand. This also carries very directly over to different time zones. So if can any of you think of how you might carry this concept of global phase, or of the relative phase, I guess, to time zones? Because you will have the same minute and second hand in different time zones. You'll have the same clock, but your hour hand will change. And so if I said, I guess, if I said this is in EST, and we want to make another clock that is in, say, PST, so this is a 3-hour difference, where PST is like, it's minus 3 hours specifically. So you can think of it many different ways. I like how Elon has suggested doing this, where you move the global reference and preserve the relative phases. So if I want to draw, I'll try to draw another clock just quickly. If we know that we've had our 12 here up at the top, and if we now want to move 3 hours backwards in time, the top would then be, I mean, if we could just think of it as the top now being, oop, that is a G, not a 9. The top is now 9, and we can draw the exact same thing, where, let's see, that's 8, 7, oop, 6, 2, 1, and this is, this over in the corner is 12, 11, 10. We can draw the exact same shape on the clock with our reference is now at 9. We have our center point. We can draw, this is, I shouldn't go all the way out, should I? This is our hour hand. We can say this is our hour hand now pointing to 7. We can keep the exact same location for our minute hand as well. So this is our minute hand. Oh, well, I guess we don't actually want to do that. We want to keep everything else. We want to keep this the same. So we need to move where our minute hand is. I have ruined my own analogy. The hour hand stays the same, but we do need to keep, we can then read off of the previous clock. So our phase is only changing our hour and our marking. So we want to read off where we are for the minute and seconds. We should go to our 2 for the minute and to the 5 for the second. And we could, of course, rotate this clock back up to be the same point. We can think of this in either way, I guess, as, oh, this stopped sharing, didn't it? Let me stop sharing and reshare. The first time I've actually caught it when it stopped sharing for no reason. Okay, cool. Yeah, I did finish the drawing correctly rather than my not thinking too hard first bit. So you could think of moving your your global phase, but then that does actually change like where your minute and second go. So you could instead think of, if you want to draw it kind of upright. I'm going to try to not go too much longer on with this analogy, but I do think it's an important idea. If we want to go back to how we've drawn this original clock, So this reference is 12. This would be 10, 9. I'm going to just draw like some of the numbers because I don't feel like drawing all of them. We can instead do our minute hand to the 2, our second hand to the 5, and so this looks exactly the same. And then we know that in EST, our hour hand is pointing to 10, and we know that we want a 3-hour difference between our EST and PST time. So we can go through the I guess EST to PST angle, which I guess is a third, 1/4 of a full rotation. So that's a pi over 2. No, yeah, it's pi over 2. It's 90 degrees. This should be pi over 2. And so by using this relative phase, the knowledge of a relative phase between these two times, we could also just draw our hour hand for PSTs. You can think of it either way, with rotating kind of your global reference and doing it that way, or you can use a relative reference to get to your resulting location. So I guess this is to make clear, this is not the correct time in PST. But yeah, did that make sense? Did this help explain phase at all? I'll give you guys a second to tell me if this made no sense. Also, are there any other questions, I guess, before we get started? Okay, not seeing any, so I'm going to move on, but you can always ask after we moved on as well, and I will stop as needed. Okay, so the topics we're going to be covering this lab are trying to locate states on the block sphere, and we're going to try to bring an analogy to latitude and longitude, and then go into how the block sphere relates to the Stern-Gerlach experiment. And then we're going to actually apply some gates to our block sphere and see how our state rotates on the block sphere with these gate matrices. And then at the end, we're going to have a little bit more on modes from last week in the optional content. And that'll be pretty quick and just like a little bit more explicit mathematical demonstration of how these modes work. Cool. So if you were in the course last semester, you may remember the same kind of exercise. But if you're trying to locate a place on Earth, how would you tell me where your hometown is? What would be your choice of coordinate system that you might want to use? Can anyone give a suggestion in the chat? Thank you to Angel and Athena and Jag and Yash and Dhruv. I'm getting a lot of latitude and longitude. So yeah, we could have our, I guess, I always forget which one's which. Longitude and latitude, maybe? And we could have, this is always reference to some location. I think it's like the 0, or like it might be the international date line that it's referenced to. I actually don't remember. It's all kind of relative. Progress. You could put this to be your 0, and then some point along the equator to be a 0, and take your thank you, Austin, for your suggestion, or for your knowledge of where the latitude, for how the longitude works. I wasn't sure where that line went from. So relative to London, so I guess that's here. So it's relative to here. We can take this to be our 0, and then we can define the distance from there and up along these lines. And I will erase my other random line that is unnecessary. Yeah, so we can choose where we can define where we are anywhere in the world with just, in this case, they're, I guess, two kind of like conformally mapped lengths. So you actually would write it as like some kind of, or you can write it as an angle or as a length. But you can have your angle up from the equator or your angle away, I guess, from this. And you can reference everything to your poles. And this is all assuming that we are on like I guess, I assume actually I don't know, because people use this for navigation for planes. So I don't know if they reference it to sea level or not. Sea level is like very standard for like standard like atmospheric pressure. But I don't know what height they actually go. I assume they probably calibrate it for specific applications. That's how we could define our location on Earth. This is often known as two angles. So if we want to do this for our qubit instead of our planet, we do the exact same thing. Or I guess in this case, like X be pointing towards the Greenwich Observatory, and this is referenced from and then our theta is referenced from the North Pole, not from the equator. But we can do the same thing to point to any point on the surface of the sphere. And I guess if we have a length for our vector, we can also have like how far away from the center we are. But for now, and I think possibly for the duration of the course, I'm not sure if we'll go into mixed states too much, but we can always assume that our R is equal to 1. So we're always on the surface, and the surface is always distance 1 away from the center, and we will always assume that unless otherwise noted. And so for this, we can define our theta on within 0 to pi for our angle, and our phi 0 to 2 pi. So 0 to pi takes us from the North Pole to the South Pole. That's pi. And then 2 pi is all the way around. So we don't need to have 0 to 2 pi for both, because we can, I guess, rotate our theta all the way around the 2 pi of phi, and that will give us the full sphere. We don't need to go from 0 to 2 pi for both. And if you don't have a good like grasp on why that is, I definitely recommend like kind of trying to like get something round or like not round, and just map out how you would use going through the whole range of angles for theta and the whole range of angles for phi, and how that gets you all the possible locations. So the reason we want to use this block sphere is so that we have a visual representation of our qubit states, because our qubit states aren't just 0 or 1, they're any superposition in between the two. We want to have, and also like we have any amount of superposition. So the value of phi, I guess, is the amount of superposition of the 0 state and the 1 state. And then our phi is our relative phase between the two states. And that gives you kind of like your location along the equator. And we'll see how that like kind of shows up mathematically in just a second. But we can define every single possible single qubit state. So any 2-level system can be defined on the surface of the block sphere. And on the surface specifically, it's for any, I'm going to specify pure state. If you don't have to know what a pure state is, I guess. But I mean, I guess the simple explanation of a pure state is everything we've worked with so far is a pure state. It is just like a single well-defined coherent quantum state. There's no like other states participating in the total state we have. And if we are in a pure state, we are always on the surface. So that's, if you hear one, it means the other. And this kind of just gives the next 2 bullet points just kind of explain what I've already said. So I'm not going to go through them again. But if we want to locate a point on the sphere, for example, if we're going through a Stern-Gerlach experiment, we shoot our electron through, and we know that, like, if it goes up here, this is we define that as spin up. If it goes down here, we define that as spin down. And we can similarly put that on the Bloch sphere, our 0 state, or our 1, 0, we can say is spin up, and our 1 state, or our 0, 1, it's our spin down. And this is just a representation. We could put this in any other, we could put it anywhere we want. Really, we can rotate the Bloch sphere any way we want, similarly to how we rotated the clock. But then we have to think about where things go in our rotated frame. So this is the standard orientation, where 0 is spin up and is on the top of the Bloch sphere, and 1 is spin down and is on the bottom of the Bloch sphere. You can think of it as the North Pole or the South Pole. Now, if we're going instead with our Stern-Gerlach X basis measurement, and we're going to, I guess, spin left or spin right, we can define them exactly the same, with the plus state here is spin left, and the minus state here is spin right. And I will say the 0 and 1 state is very, very standard, but like the plus and minus state, people do draw their Bloch sphere rotated by 90 degrees pretty regularly. So if you do see something that like is rotated 90 degrees from what you're used to, it doesn't like matter so long as you have each axis defined. Sometimes, like, generally that's because they've switched their X and Y axes. So you will occasionally see that, like here we find this as X, but sometimes you will see people instead just like do, this is Y and this is X. But we're going to be using this convention as consistently as we can, where the one pointing out of the plane is X, and the one in the plane, or the one like within the plane, is Y, just for consistency. But this is just the exact same representation placed onto now this sphere that allows us to describe all these different superposition states. So if we go through, I guess, both the x-axis and the z-axis, and we have this kind of like arbitrary angle, we will have our electron like projected into the x state, or yeah, once we go through, like we could be in any random angle here, but it will be projected into the left and right states after going through this first x measurement, like we said. And then when we go through the z basis measurement, each of these states will have a 50-50 likelihood of being measured as spin up or spin down. And so we will always, if our final measurement is in the z basis along the z axis with the Stern-Gerlach experiment, we will only measure spin up or spin down. We're not going to be measuring spin right or spin left or anything else, regardless of what we put into our Stern-Gerlach experiment at the beginning, or what we got out of this x basis measurement. So we can show this mathematically, and we're going to try to have like a little bit more explicit math, but not go into it too in depth for this, where our plus state or our right state can be taken as an equal superposition. You can see this 1 over root 2 of our 0 state and our 1 state. And this gives you the exact same thing as what we always write. So like we have this written in like a more compact form a lot of times, versus 1, 1 normalized by root 2. So if we instead do this with our minus state or our left-facing state, then I guess I may have written left and right backwards a couple slides ago. I will fix that before I upload. We can do the same thing where we decompose it into an equal superposition, but we now have this minus sign, which, if you remember, is equal to e to the I pi is equal to -1. I have a mug that says that on it, so I never forget it. And it does the exact same thing where we can take this as 1 over root 2, 1 minus 1. And that is our minus state. But when we're actually measuring, we are measuring these two, and we are then using this to reconstruct the state that we actually had exiting the x-axis, and then can again reconstruct the original state we had. So with the block sphere, the mathematical description for any quantum state, psi, is a function of our angle theta and our angle phi, and this is the formula we use for it. So it's this. Then this is what I mentioned it a couple times, that all of our angles are reduced by a factor of 2. So that's why when we say we do a pi pulse or a pi over 2 pulse, it is off by a factor of 2 from how much we've actually rotated on the block sphere, because we have this factor of 2 scale. And if you have ever seen a sphere that does not have this, it is called the Raman sphere, or the Riemann, I never know how you say it. I think it's Raman sphere, and it's what mathematicians use. This is the physicist's block sphere, people call it, but mathematicians do not use this extra factor of 2. And so if anything you see is ever inconsistent by exactly a factor of 2, that might be why. So again, these angles can be within this particular range. And if we want to, I'm going to do 1 to 10. So we're going to do for 0 first, what is theta and phi for our 0 state? And we know our 0 state is pointing straight up right here. It's not too difficult to read off if you are familiar with your sines and cosines, but it can get confusing if you are not. And you can just plug in. I'll give you a bit of a hint in case you've forgotten that you want to end up with that. So you're going to solve for psi. Why did I try to write another psi? Psi theta phi is equal to 1, 0 is equal to cosine theta over 2 e to the I. This symbol is also the exact same thing as this symbol. It's just 2 different ways of writing phi. Sine theta over 2. And so we can also solve this as cosine theta over 2 is equal to 1, and e to the I phi sine theta over 2 is equal to 0. So we can do 2 solved values. I'm getting some things in the chat. I'll wait for a couple more people to send something in. And if you want to kind of do the inverse solve, I guess this this angle here, I would take that only as anything that gives you a phase. If you're just looking at a real number, not an imaginary number, you haven't gotten any random signs. I mean, you kind of want to solve this. You solve this to get theta. So the first step, say step 1. I feel like I kind of threw you guys to the wolves a bit with this problem without giving you steps, especially because I know a lot of you have not done a lot of trigonometry before. You want to solve arc cos, or like cos inverse of 1 times 2 is equal to theta. And then you take this theta, you plug that into here, and you solve, I guess, I don't know how to do this. Yeah, we'll just like, this, we're just gonna ignore that. So this is just 0. Well, I think we actually don't have to do anything, because since it's just 0, we don't care about the sign at all. The sign, not the sign. Sign meaning plus or minus. If we plug in the result of theta into this, we then want to just plug in our resulting theta that we've already calculated here and see what we get. So to give, like, so I've gotten, thank you to Elon and Athena for your answers. So to give kind of an overview of how, like, of what you get with this, I guess, when you want to get your I guess cosine to be equal to 1, and cosine of 0 is equal to 1. So we can just take our cosine to be 0. It could also be 2 pi or whatever, but we want to concatenate everything to less than 2 pi. We don't, like, that's what this is not inclusive, so we don't actually want to go to 2 pi ever. Oh, why did I draw 2 arrows? Not inclusive. That's what this little parentheses mean, and this means inclusive. So we are not allowed to actually have 2 pi. We're only allowed to have 0, and we're allowed to have pi, but we're not allowed to have 2 pi fully. So you can plug this into a calculator, or if you just know it off the top of your head, you know that arc cos of 1 is equal to 0. 0 times 2 is 0. Therefore, theta is 0. And then sine of 0 is also 0. So we've already gotten this to be 0. We can put our phi to be anything. And it doesn't actually matter what we choose for it. Generally, if we are on the north or south pole, it will never matter what our phi is. We're not going to be able to see the effect of phi, because phi is most well defined along the equator. So, like, that's one thing that we can note is always the case. So that's our 0 state, and I've already kind of made a mess this slide. Do I have a copy of it? Let us find out. No. Okay. I'm going to do the same thing on the next slide for our plus state. Now, I said plus state, not minus, right? Okay. So I'm going to do our plus state, and we know that our plus state is equal to 1 over root 2, 1, 1. And on the block sphere, I guess we've put the plus state to be here, where this is our x-axis, this is our y-axis, this is our z-axis, and we can define theta as coming down from here, and phi as coming over from here. It's all correct, right? Okay, cool. Then we want to do the exact same calculation where we set, we know our psi of theta and phi is equal to 1 over root 2, 1, 1, which we know is equal to cosine theta over 2, e to the I phi sine theta over 2. And so we're going to do the exact same thing, where we take the top line first. And so we know cosine theta over 2 is equal to 1 over root 2. So that's just taking this top row. And we can do the inverse of this, where theta is equal to 2 arc cos 1 over root 2. And we can calculate that. Does anyone want to give me the answer to what theta is. I've given you the formula. You can plug it into Google and Google will tell you. And I promise they will tell you the right answer. Nice. Yeah, so, well, yes, I've gotten a lot of correct answers, I guess minus, plus or minus the factor of 2. So you can see on the block sphere that I guess we are, let me think about how this actually works. I think the theta work, I'm not sure if I've actually written, or we've definitely written this right in some form, but I don't know if we've drawn it correctly on the block sphere. Because, let's see, arc cos 1 over square root 2. Should give you like pi, right? Or pi over 2, and then when you multiply you get pi, but then pi is all the way at the bottom. So I think this should actually be theta over 2 here. I'm not 100% though. So I'm going to think on that and correct later, but because I know like the plus theta is obviously along the equator. When we actually calculate this, I believe we are off by our factor of 2. Let me just like get my calculator out, actually. Okay, but wait, yes, the result should be pi, never mind. Okay, I am totally off. Some of you guys gave me pi, some of you guys gave me pi over 2. This should be pi over 4. Okay, now everything makes sense. Okay, this is correct. This in of itself gives you pi over 4. Oh, not pi over 2. Oh my gosh, now I'm doing it. Pi over 4. And then you multiply that by 2, and so your result is pi over 2, and that gives you the correct location on our block sphere going down. Great. So that's step 1. And now that I'm far less confused, we're going to plug that in to our sine and get the value like that we should get out for our sine, which I guess I think is also just going to be 1 over root 2. But I will do it with my calculator to make sure I do it correctly, so I don't confuse anyone, mostly myself, because I seem to be confusing myself tonight. And so that's going to give us pi over 4. Yeah, and that should give us also square root of 2. So sine theta over 2 is equal to sine pi over 4 is equal to 1 over root 2. I'm sorry for like working through all this math like in great detail. I think it's useful to just go through it a couple times because it can be quite confusing. Clearly, I have already managed to confuse myself by the factor of 2, even though I know that it is there and what it should be. And then for our final step, we know that our EI phi sine theta over 2 should give us 1 over root 2. And we know we already have 1 over root 2 here. So we want our we want our e to the I phi term to not give us any like i's, any negative ones, anything. And to achieve that, we know this is 1 over root 2. We can kind of by process elimination, we know that e to the I phi should be equal to 1. Therefore, phi should be equal to 0 because e to the 0 is equal to 1. And so we have now solved the second problem with great struggle on my part. That's our solution. Okay, did that make sense to everyone? So, okay, I think I'm not seeing any super confused questions in the chat. Can also, I will upload these to Canvas so you guys can work through them again with like kind of the guidance. And there's also like, if you Google like block sphere, you should be able to get these same results pretty easily on Google. Shouldn't each the I-phi equal 1/2, not 1? I don't believe so. So I think if you plugged in into your calculator this, and you may have gotten square root of 2 over 2, which is the exact same thing as 1 over root 2. It's just like rational or whatever. But yeah, we don't have this factor of 2 term on our phi. We only have it on our theta. So if you are off by a factor of 2 on your phi, you have tried to correct for something that you only need to make sure to correct for on theta. Hopefully that answers your question. Yeah, if I'm not seeing any more questions, so I'm going to try to get through the remainder of the content because I feel like I've gone through this for quite some time, and we have a lot more problems they told us to go through, but we're not going to go through them in this much detail. So now we're going to go on to quantum gates. So when we want to, so we have put single qubit states on the block sphere, but now when we're actually doing computations, we want to change these qubit states with our gates. So if this kind of has this like random example of just like searching a list, and we need to change our state to our final value such that we complete our computation and get the solution we're aiming for. So when we apply these gates, we've already gone through like the very common like X, Y, Z gates, but we're going to show how these gates can actually be generalized to be a certain angle rotation around the block sphere. So our X gate is a 0, 1, 1, 0 gate, but we can also do a generalized version of this called an RX gate. So it's a rotation around the X axis. So to be clear, it goes around this axis, I guess counterclockwise. And the generalized form for this is cosine alpha over 2, negative I sine, et cetera, et cetera. You can read it off. It's a little bit more complicated to write out. So to give an example of this, if we want to apply an RX gate to our 0 state and we want to rotate it down to our 1 state, what alpha do we want for our rotation? Oh, and I'm seeing a I'm seeing a math for if your e to the I phi times 1 over root 2 is equal to 1 over root 2, then e to the I phi, like you can divide 1 over root 2 on both sides, and then you'll end up with e to the I phi is equal to 1. In case anyone else is confused on that. But yeah, so it should be 1. I'm confident in that. But yeah, these factors of 2 are very, very hard to deal with. So definitely do not be concerned if you miss them very frequently. I like literally missed one just now. No problem. Okay, great. So I'm gonna give you guys another second to try to work through this. It's a bit overwhelming, I guess. But a trick is you can see that our X gate does the same rotation that we want. So if we want to solve this such that cosine alpha over 2 is equal to 1, which is what we want to do. We know that's what we want this to be equal to whatever 1, 0. Wait, that's not right. We want it to be, we want the sign to be, oh my gosh, why does it, oh, every time, oh my gosh. Okay, sorry, I am just struggling today, clearly. There we are, we're back. It'll be 0, 1, 1, 0. I'm going to, oh, no, it won't let me erase. Oh, because I can't erase anything. I'm gonna get rid of that. Okay, I want this to be 0, 1, 1, 0. So we want our negative I sine alpha over 2 to be equal to 1. So how do we get that? Well, one thing to note is that the relative phase, like this I term, doesn't matter. So we're going to ignore this. We're going to pretend this isn't here. And so we're just going to solve for sine alpha over 2 is equal to 1. And if you're confused as to why we can ignore it, think about where we are on the block sphere. We're pointing here. If the angle that we're at is anywhere around the entire equator direction, we're still pointing directly orthogonal to the equator. And remember, with all of our dot products that we went through last semester, if we are orthogonal to something, then we don't see any results of those two vectors interacting. So we can be at any angle in our like equatorial plane, but if we're pointing purely along one pole, we don't see that effect at all. So that's how we can ignore this phase. And that's how this gate is defined. It's defined with this phase because technically you do accumulate this phase, but since you're still pointing in the same direction, you don't really care. So we want to solve for this sine alpha over 2 is equal to 1. So equivalently, alpha is equal to 2 arc sine 1, or I guess we could also, actually, do we need to have this and have this? We could also, I guess, maybe I shouldn't get rid of this term. I may have been incorrect doing this. We could divide this by our negative I, and that's equivalent to giving us I, and then arc sine of I. Wait, I don't think we can get an imaginary number off of this. Let me think through this. I normally don't work with these gates with these phase factors on them because they confuse me, and I always forget how you're supposed to treat them. Yeah, we don't need this I. We definitely don't want this I. Get rid of it. My first statement was correct. We get rid of the I. There. And then we do arc sine of 1, which gives us pi over 2 times 2, which gives us pi. So alpha is equal to pi, and we have solved this first thing. And this is why we often, like, I may have said this because it's like intuitive at this point, but that's why we call a like, I guess, like state flipping operation a pi pulse. A pi, it's a pi duration, like this alpha is equal to pi, and it goes from the plus z direction to the minus z direction, or vice versa. So similarly, I may have said at some point, well, I think we're going to solve it in just a second. So I'm going to go to the next slide, and we will do the same thing, but with going around. We're still going to be doing an Rx gate. We're going to be going this distance, alpha. So in exactly the same way, we now want to, I guess, create the right like value on each of these. So if we're starting in, well, I guess I'll just go and write out the equation. This is like quite complicated math we're trying to go through like in a lab. So if you don't follow everything, I'm very sorry for going through like so much math in such a short amount of time, but definitely work through it afterwards. What we want here is 1 over root 2 negative I over root 2. that's the exact same thing as this equation here, is equal to cosine alpha over 2. Sorry, that's kind of hard to read. Negative I sine alpha over 2, negative I sine alpha over 2, cosine alpha over 2. I'm going to try to keep my parentheses consistent. And this is times our original 0 state. So we know what we're going to get in either case is we can solve like each kind of line of this. I'm going to write that, I guess, at the top, that this first line here, this is equal to 1 times this cosine alpha over 2 times 0 times this negative I sine alpha over 2. So we have our 1 over root 2 is equal to 1 times cosine alpha over 2 plus 0 times negative I sine alpha over 2. And so this is 0. So all we actually want to solve is the same thing we solved before. I think like actually the exact same, where we now have 1 over root 2 is equal to cosine alpha over 2, which is the same thing as arc cos, or let me write it out in a prettier way. Alpha is equal to 2 times arc cos 1 over root 2. And we've calculated that before. We know that this term here is pi over 4. Therefore, alpha is equal to pi over 2. And so with just solving one line, we've already solved the whole thing. We can double check to make sure that we get this correct value for the second one. So that's your homework, is solve this second line here, which this second line is negative I over root 2 is equal to 1 times negative I sine alpha over 2 plus 0 times cosine alpha over 2. And if you're confused as to where I got that from, I just did the matrix multiplication of 1 times negative I sine alpha over 2 plus 0 times cosine alpha over 2, and then it equated the whole thing. So just regular matrix multiplication, and then I took each line separately because we know each line separately has to work out. And so we can quite easily, since we only have one free variable, we have like an overdetermined system. And so we just have to solve one line, and we see that alpha is equal to pi over 2, and you can solve this equation just the same and see that alpha ends up being pi over 2 in either case. And this is very often called, because of this, a pi over 2 pulse. A pi over 2 pulse always puts you from a pole down to the equator. And so even if you don't know how to work it out, all you have to remember for like honestly a massive portion of gates is that a pi pulse goes from 0 to 1, and a pi over 2 pulse goes from 0 to the equator. Or yeah, I guess from like either state that you're in to the equator. I'll always rotate you to the equator. So now we want to give one final example, and I'm going to make you guys work through it yourselves. I'm just going to sit here and wait until I get answers rolling in the chat. And we're going to now apply the y gate. So this is our standard y, like Pauli y gate, that is defined for a full pi pulse. And the difference between the x gate and the y gate is the y gate goes around the y axis rather than going around the x axis. So if we are going from up here, we're going down, we go down to the x, we go down to actually being aligned with the x axis and then all the way back around. So with that, we're going to do our generalized y gate, which is written like this, with our beta angle coming down from the z axis around the y axis. And so now, kind of given a bit of a hint as to how to do this, but if we apply the ry gate to 0 and want the final state to be 1, can anyone tell me what beta should be? And I kind of already told you the answer because I'm bad at keeping secrets. Also, it is 9 p.m. So if anyone has to go, I'm very sad to see you go. As usual, I'd be sad to see you go in 10 minutes once we're fully done. But of course, I cannot keep you any longer. This lecture will be put up on YouTube, so you can watch the remainder of it if you wish, or if you just prefer to read the slides, those will be posted onto Canvas. But yes, back to problem 3. Yes, you can access this. Well, you can't access Zoom with me on it another time. I'm only on Zoom for my allotted few hours a week, but it will be on YouTube. This explicitly this recorded lecture will be on YouTube, and my annotated slides I will post on Canvas. Okay, not getting any values for beta, and I'm very disappointed. Ooh, I got one. Thank you, Austin and Kazi and Jeffrey. I don't care how you guys got these, but oh, and Jade, and Jade and Surya, Snehil. Yes, beta should be pi. And I told you that going from 0 to 1 gives you pi. You can also, I guess, calculate it if you so wish, where we know that sine beta over 2 needs to be equal to 1. And so we can back that out such that 2 arc sine of 1 is equal to beta. And that gives us pi. Yay, we did it. It's much easier when you don't do all the math yourself and you just kind of know what you should get. Because you'll do the same math over and over again. You'll get very used to it. But if you're doing an arbitrary angle rotation, then maybe you want to calculate it explicitly. But for this, we know what we get. Amazing. Similarly, if we now want to go to a plus state, so you will remember the plus state that we often discuss is actually normally like a Hadamard gate. We actually do, normally people describe it as a Z or a X rotation than a Z rotation, because Y rotations are less commonly implemented for some reason. You can also do it as a Y rotation of this angle. Does anyone know what this angle would be? And we can also, I guess, so I've mostly been like, okay, we're going to do the math for it, but we can also kind of read it off. We can see that we want this angle going down here to be 90 degrees, which is equal to pi over 2. So we can do it that way as well. But that's less fun. That's like way less fun than doing the math. So do the math. You'll never get it wrong if you do the math. You'll sometimes get it wrong if you try to draw it, because drawing is hard. Yeah, thank you to Surya for posting your solution. Okay, so now I'm going to do graphically the Z gate. So this is also a good reason for why we use the block sphere is you don't have to do math. You can just look at the block sphere and try to figure out where you're going. So now we have our Z gate, which I guess you saw is accruing a phase on the on our 1 state, but not on our 0 state. Remind you that like our 0 state is this, and our 1 state is this. You can see that this 1 state will be affected by our -1, but the 0 state won't. So we're adding a pi phase on our 1 state. And so we can now go to our more general, our Z gate, where we're now doing this an e to the I gamma term for this this angle that we are accruing. And so if we apply an RZ gate to our plus state, which we've taken to be here, that's our plus state. We want to go whoop all the way around to our minus state. You can calculate it explicitly, just like I showed, where we want our result 1 minus 1 to be equal to e to the negative I gamma over 2, 0, 0, e to the I gamma over 2 times 1, 1. This is 1 over root 2 multiplied by it. You can solve this, or you can look at the block sphere and you can see we've gone from here to here. How far is that in angles? I'm sure many of you guys know this. So I'm sorry for like torturing you so much with the math, but I think it's a good illustration of how useful the block share is, because you can just look at it. Great, thank you, Elon and Athena and Angel and Sahil and Kazi. Yeah, you guys have all got it in one. This is a pi angle equal to 180 degrees. So we very easily gone from I guess one side to the other, did not have to really like think about it too hard at all. And if you want to see the math, I'll do one quick math just for you. We can solve the top line of this, or I guess like we'll take this 1 times this e to the I gamma over 2 root 2. So we have this 1 over root 2, 1 minus 1. Or wait, I'm not gonna do the whole thing. We're going to just do, go away. There we are. Okay, times, we're just gonna take the top line. So this is gonna be 1 times e to the negative I gamma over 2 times this 1 with a 0 times this 1. And this is times 1 over root 2 in total. So we can cancel these out. And then we know e to the negative I gamma over 2 is equal to 1. And so the value that you need to get for this, I guess, since it's, well, since it's, this is not, I guess pi over 2 times negative I will also give us, so this is a degenerate problem, I guess. So we can have multiple solutions to this, but we should end up with pi. Let me try doing the other line just to see if it makes it a little bit more clear how we get to the right value. So this is negative square root 2. And we can do the same thing with this being equal to 1 over root 2 e to the I gamma over 2. And so we can cancel these out, and we know that we need e to the I gamma over 2 to be equal to negative 1. But this, in general, am I off by a factor? I don't think I am. This to me would give me gamma, like, so you want e to the I pi is equal to negative 1. Now I've confused myself. Oh, we're over time and I'm confused. Oh no. I know, so we can do this, like, I guess explicitly, instead of like being like, oh, I know what this value should be. We can take the log of both sides and say that log of negative 1 is equal to I gamma over 2, or equivalently, I'm just like drawing everywhere now. Gamma is equal to 2 ln negative 1 over I. I'm going to try doing that so that I don't confuse myself. We take ln of negative 1. We get pi I. We divide this by I, which is what I thought we should do. Then we're multiplying it by 2, and now we're at 2 pi. That's what I keep getting. I keep getting 0 or 2 pi. So I don't know why I'm getting 0 and or 2 pi. I don't think we should be getting 0 and or 2 pi, but I couldn't tell you where I'm going wrong. It's possible I'm just like, oh, wait. I think we should get, okay, this is still a pi duration, but this is a half angle. So then this makes sense that gamma is equal to 2 pi, but then the actual angle we process over is gamma over 2, which is equal to pi. Okay, I've convinced myself. That's how we should end up with this. The reason why we end up with this being wrong is for the same reason, where we end up with 0, which is equivalent to 2 pi. You can't take the ln of a negative number unless you know tricks. So a lot of a negative number is always going to end up with some like phased term. You're going to end up with an imaginary number. So there's actually just lookup tables for logarithms of negative numbers. You can also have like lookup tables for like just this bit. You can take it either way, but there is like a well-defined value for this. But yes, the trick for how you take a lot of a negative number is you just know the answer with these lookup tables. And very smart mathematicians have proven how each of these work. But it's not something you can like analytically calculate easily. So I'd recommend against trying and just looking it up. Yeah, cool. So with that, we have our key takeaways that we can use the block sphere to represent any single qubit state. We can apply rotations to the block sphere, or apply rotations to a single qubit, equivalent to rotating the qubit on the block sphere. And we can do these arbitrary angle gates that you can take kind of like common values of to get your X, Y, and your common like Pauli X, Y, and Z gates. So with that, next week we will be doing IBM quantum experience, this on, I guess, like just with their GUI, and then we're going to be using Qiskit in 2 weeks to actually write Python code to control these gates. This is just going to be drag and drop next week with like a GUI, and then we're going to actually write code in 2 weeks. So definitely make sure to sign up for IBM Quantum Experience. We do have further reading available. This is, I believe, Umesh Vazirani is at Berkeley. It's a 3 blue 1 brown video. And then Scott Aronson is actually at my undergrad at UT Austin. He used to be at MIT, but since we apparently hate each other so much, I started graduate school at MIT, and he moved professorship from MIT to UT. Like I was a year apart, so there was a year when he was there at the same time as I was, but it was pretty funny. Okay, are there any questions on the material so far? I'm going to go very, very quickly through our optional content, and I'll start the post-lab Zoom feedback. Hopefully this made some sense to you guys. I know I had like a lot of like mathematical like attempts and screw ups this time, because I can't do math on the fly even when I've rehearsed it beforehand and I know what result I should get, because I do know the results that I should get, and that's why I confuse myself when I get factors of 2 off, because I know the answer. Yeah, if there aren't any questions, I'm going to quickly go through just our eigenfunction example with some music. And I don't know if you'll be able to hear it well. So like we showed last week, this ripple can be reconstructed by adding up many, many different modes. I guess primary mode, second order, third order, etc. When we actually do this, and I'm going to take out my you will be able to hear the music if I can figure out how to switch. Okay, we're gonna see if you guys can actually hear this, because I'm not sure if it works well. Oops, that was the wrong way. Okay. So we have, oh, that was very, very quiet. I will try to make this as loud as possible. This is a piano sound. Oh, that was still so quiet. Okay, I don't know how best to make this louder. Wait, could you hear that at all, actually? I have it, oh, it's supposed to play through my speaker. Well, this is as loud as it's going to go. Well, if you can't hear it, I will upload these. I can only hear it quite faintly. We can also do a version with the violin. I don't even know where it's trying to play. It's doing its best. But I put it through the MacBook Pro speakers, and I still don't hear it. Oh, there it goes. Okay, that's louder. That is a violin. I think I was told it's an A4. And this is the piano, the same note. Okay, cool. Audio is hard. I struggle with it every day. Okay,
So, okay, so we can also, we can take what's called the Fourier transform of these modes and actually get the frequencies of both of these. And you can see that even though they're the exact same note, the same, I guess, like fundamental frequency, which is this guy, the fundamental mode is this one right here. The amplitude of each of them, the relative amplitudes, are very, very different, where the fundamental mode is very small for the piano, but very, very large for the violin. And similarly, we have these higher order modes, second order, third order, and this is like kind of a fourth order that's a little bit noisy. For the piano, generally like a violin, I guess, gives a more pure sound, a more pure note than a piano does. I don't know if that's always true, but in this case it is. And which you can see by this being like a little bit noisier. And we get very, very, the majority of our sound is our primary mode, our fundamental mode with our violin, and then less with our second order mode, our second harmonic, almost no third harmonic, and then fourth harmonic has a bit. And this actually goes up to many, many, many higher frequencies, and you can back out all this to have your total energy work out to be like, I guess, I don't know if it would be 1 on this scale. I don't know how Akshay scaled it. You can see that it's the same note, it's the same frequency, but because it has these harmonics, these higher order modes that are like multiples of that frequency, it can be different in how it is distributed in power. So you can see this just kind of writing out what each of the modes are with our fundamental, second, third, fourth order harmonics. And this is really just showing how that's why we get these different sounds from these different instruments, is because the relative contributions of the different modes or the relative amplitudes of the different eigenstates are different. And so in the same way, we can change the relative contribution of the eigenstates of the qubit and change the qubit state or the wave function. So when we do a rotation on the Bloch sphere, anytime we're going, I guess, along the, I'll draw the full thing. Anytime we're going along the surface, like around the x or y axis, we are changing the relative contributions of the two eigenstates. And that is changing our total qubit state in the exact same way that it happens with a piano versus a violin. Okay, so with that, made it through all the content. We are down to like half the original class, which of course, thank you all for staying late. You're never obligated to, especially if you have things to do in the evening. Are there any, I'm trying to go back to my questions slide, but I'm not quite making it. Are there any questions about the content for this lab? I can take like 1 or 2 questions if there are any. And if not, I hope you all have a wonderful week. I hope this was helpful. I know there was, it was a little bit rougher than usual. I'm not used to having to do math now because I haven't had to do it in like a month. But yeah, thank you all for coming to lab. Hope you have a great week. I guess I'm not seeing any questions, so I'm gonna stop sharing.